I'm Rahul Malik. I'm an iOS engineer on the core experience team. And what our team focuses on is building tools and infrastructure and frameworks to make the rest of Pinterest go faster. Now, the iOS team at Pinterest is, wait, hold on a second.
Yeah, if you push this one, good. Yep, there you go.
All right, cool. The iOS team at Pinterest is a little bit over 50 engineers right now. Over time, we've added about 700,000 lines of code into the code base. And during business hours, a commit lands around every 7 minutes. So a big challenge we have is how can we enable our team to move fast with quality? And there's a lot of ways you could accomplish this, but the most fundamental way of which that we've approached it is the build. So today we're here to talk to you about the hacks and tips and more or less our year-long exploration in 45 minutes of putting the iOS app on Bazel. So our iOS app has a lot of similarities as other apps. We have our application, which has a production and beta version. We have a series of extensions. We have a share extension, a Siri extension, and some extensions for notifications. We use Cocoapods, like a lot of other people. So, and in fact, we have about 50 plus third-party dependencies. Unlike other apps, though, we also have our own custom clang toolchain, which we use to support things like custom static analysis to enforce our own best practices. And we also have code generation through Thrift and also through our own in-house generation tools like Plank. But as the organization has grown, we've certainly had our scaling challenges. And I'm sure everyone can understand this one. Add more developers, more code keeps going in, build times start to increase. The CI is also struggling to keep up with it. And the needs of our CI have also grown over time. And last but not least, we have a lot of it works on my machine issues where I'm sure everyone here understands that one. So basically where you're like, oh, CI failed, but it's passing locally. Let me just dig into that one log on the CI build machine and figure out what happened. And at the same time, we're also trying to figure out how to scale our architecture. And we had this initiative we started at the beginning of the year called PinCore. And what PinCore is, it's the transition for us into a modular architecture. It's us actually taking one single monolithic app and breaking it up into a series of frameworks that represent things like logging or networking or just common core functionality. And so what this does is it allows us to create a set of well-defined, documented, and tested modules in our app and for other apps we might create. And it also allows us to encourage reusability. So it allows us to actually dictate clean interfaces and actually have good conversations around does something belong in a certain module or not. Now, given that we were having these scaling challenges and we were trying to take our architecture to this modular architecture world, we had a set of goals that we came up with for our build system. First, and this is why we're all here, fast and reproducible builds. Second, we wanted to take out the it works on my machine problem. So we really wanted to focus on sandboxing our developer environment. And the needs of our application are changing every day. We use code generation with Thrift right now. Maybe we're using gRPC in a couple of years. That's a plug for you guys. And it's like you don't know what's coming next, and we need a system that can adapt with us. We ideally want to save our developers time. We don't want to rebuild things that you already have built. And this is kind of one of the more important parts is we need something we can actually kind of dip our toes in. We need something that we can incrementally adopt because it's a large investment, especially for a team like ours, to say that we're going to spend the entire year, even though that's what we take the entire year and change the entire build system before we start to understand the benefits, before we start to understand how this all works. But how do we actually build modular components in our build system? And how do we actually improve the reproducibility of that system? When we first started to set out, when we first tried to build different frameworks, one thing we started to do was look at our existing tools. If you're familiar with iOS, Xcode is like the de facto build system, editor, and configuration management system. So we started by seeing what would it take to do this. But we already had some issues with Xcode. First off was reproducibility. On our CI machines, we had to clean before every job because we couldn't actually use the build artifacts from before. If you try to maintain more than one target in Xcode, you've had to change configurations and manually propagate them and try to figure out if everything's reflected correctly. And you can't script that at all. And then it's also lacking extensibility. You can't have code generation tasks that yield new files. It's hard to integrate other tool chains into your build system. Then the next thing we said is, so our third parties are managed with Cocoapods. So let's see if we can start to make our frameworks with Cocoapods, which has better configuration management. You can script all the configuration changes with Ruby. But it generates an Xcode project that had the same reproducibility issues, so we wouldn't get any of the wins on CI. And furthermore, we encountered modularity issues really quickly because we set a goal early on that we wanted to maintain a sort of like a mono repo for our iOS code. So even as we broke apart different modules, that they still existed within the same repo. So we weren't doing things like committing to one repo and then bumping a version in another one and trying to manage sort of dependency hell. So but when we tried to make local dependencies depend on each other in Cocoapods, we quickly hit a wall. Then we went to the one our friends down the street, Airbnb, were using, Buck. Buck, I'm sure many are familiar with. It has the promise of sandboxed and reproducible builds, and I believe it delivers on that. But for us, there was really not a great path to incremental adoption. We were trying to build a subset of our application using Buck, but building multiple architectures involved actually like hacking within Buck, producing our own custom fork. And we decided at the same time that we came across Bazel, and we didn't want to do that. And it is extensible, which is great, but there isn't an equivalent like Skylark. So that you get things like macros, but if we want to have custom rules in our toolchain, it wasn't exactly as easy. So this got us to Bazel. And Bazel was really appealing to us because it had this incremental adoption story. We were able to use like existing rules like Apple Static Library to build these fat architecture binaries that we could use to release our app. And we actually started to do that really early on in the year. It allows us to define all of our dependencies, their versions, and exactly what commit they're at. In our build system so that we have completely reproducible environments between CI and local builds and also between developers' machines, which can vary. And it's extensible for the future. We take advantage of things like custom tool chains with Clang. We do our own code generation. So being able to actually have those as part of the build is really powerful for us. And we're excited about the future of Bazel. We're excited about remote execution. We're excited about caching. You can't cache an iOS app completely yet, but we're working on it. And to tell you a little bit more about how we started with this, I want to bring Brandon Case up here to talk about incremental adoption with Bazel.
Hello? Can everyone hear me? All right, cool. So incremental adoption. Yeah, so as Rahul was saying, we wanted to sort of move slowly into Bazel, and we had this nice set of libraries that we were making with PinCore. So we're like, all right, let's build PinCore into one big static library, and then we can take that and sort of stuff it inside Xcode and just let Xcode do its thing off of there, right? So that's pretty easy, right? We all know how to do that. We just do Bazel build, and we point it to a target that can build a static library, like a fat static library, and then we're done, right? And we even get like the IDE experience from Xcode sort of for free because of Tulsi, which is another project by Google, where Tulsi can take your build configuration in Bazel and produce an Xcode project. So that's nice. So really, the only thing we needed to do, sort of, right? It turns out not, but like I'm trying to do a story here or whatever. Is teach Xcode about the artifact, the static library, and this, I'm going to say, this is before the -- experimental -show -artifacts flag, for those that know about that, or at least before we discovered it. So check this out. So this is a snippet from a shell script. Look at that second line there. So all right, we need to get the static library, OK? So when you do a build with Bazel, there's a Bazel -out folder at the top level of your workspace. And then under that is a bunch of subdirectories. And they're there's like a lot of them. And the names are weird. So let's just sorted by reverse timestamp and take the first one. And that almost worked, sort of, but like we have some other greps, because like it wasn't good enough. So obviously this is like really terrible, but it worked enough. Yeah. So, and then at this point, like it should work, right? All we had to do was find the static library. Sure, we have like one hacky thing, but then it's all gonna work, so it doesn't matter. But then we forgot about headers, right? Or we were thinking about them the whole time, but in this story we forgot about them. So right, so it doesn't compile because we didn't do anything about the headers. There's all these headers in our libraries, right? And unfortunately, on iOS, there's this convention, this very unfortunate convention, where all external and internal dependencies on libraries are imported with the angle bracket style system includes, where it's the name of your framework or library or whatever / your header. Okay, and even if the header is nested deeply in subdirectories, it needs to be accessible like that. And it needs to be accessible like that because all of our developers rely on that, depend on that, are familiar with that, and all developers of third-party dependencies do that. And we, as Rahul was saying, we had like 50, we have more than 50 of those. So, so this was super important. And there's like a lot of different ways that you can handle this, and I think Jerry's going to talk about some of the better ways to do it. But at first, the sort of easiest way, right, or the most trivial way, is to just put the headers in the right spot, right? So we have some more nasty, disgusting shell script stuff where the header depths variable is like computed from Bazel query. So like that part's great. And then we like awk and stuff, and we make a directory under this platform include, and then we can just sort of like go over all the headers and move them into the right place. But we actually want to symlink them, not move them, because we want to be able to edit, at anywhere, and the edits propagate, whatever. It's like all shell, all disgusting, all bad. But it builds, right? So so whatever. And then and then we're like, okay, so we're done. But we're not done, because this happened in Xcode. So what you're seeing is a snippet of the sidebar in Xcode, and when the files are read, it means that they're missing on the file system. Okay, so what's going on here? So Tulsi, remember, takes our Bazel build configuration and generates an Xcode project for us. So we didn't have to do anything, right? But for all the generated code in our build, like Rahul was saying, we depend on some generated code. Well, Tulsi says, okay, well, generated code appears in the Bazel-gen files top-level directory. So why is it missing? Why are all of our generated code missing, right? And it's because in Bazel right now, when you do a build and you feed it a label, right? If that specific rule doesn't generate files, then they will be missing from the top-level directory, even if transitive dependencies are generating those files. So, right, let's just, everywhere we invoke Bazel builds, include all of our rules that generate files everywhere and never miss one. Because if we miss one, then our developers will be sad because red files will appear. And Xcode sort of freaks out. But if we do that, then we're sort of done, right? Because now the files are there, people can edit, and it builds. But then it's not really there. It's only there after we do a successful build of our framework, or all of our libraries, right? But we don't want to wait for our entire build to finish before people can see our code. So let's make like a make target that just does Bazel build on the generated, all the generated code labels, and then whatever, right? So you can see like what was going on here. Okay, so we're trying to incrementally adopt Bazel, and we built on top of these, like what was supposed to be one line of shell became many lines in shell scripts that called shell scripts. And there's this sort of meme of like build pincore.sh is this nightmare. So if other people are interested in this incremental adoption, which I think is sort of useful, if the Bazel team or all of us open source contributors could do some things, it would be a little bit easier, I think. So first of all, the --experimental-show-artifacts, what that does is it dumps all the artifacts that are produced, or the path to all of the artifacts that are produced, so you can easily extract those. So that's super good. We're happy that that exists now. If there were a way to say like, hey, I'm doing this build, but like don't hide all of the generated code, please, because some people want to look at that. That would be cool. And then a lot of examples would be really, really great. I think we struggled a lot because of things we just didn't know really existed in the beginning, and we hit these roadblocks that we kind of, obviously we had to hack over. So, right. So we did this, and like this sort of like was okay for a few months, honestly. But there were problems, as you could probably imagine. So we decided we should just go full Bazel. And things hopefully will be better, right? Because everything is all together, We're not kind of like hacking this thing out of Bazel, right? So let's talk about going big. And to do that, I'm going to invite Jerry Marino. to talk about that stuff.
All right, thank you, Brandon. That was awesome. Cool. So yeah, I'm going to tell you a little bit about going full Bazel. But first, I want to give you a little bit of background on the Pinterest iOS app. And so we currently have about 50 external dependencies in the Pinterest iOS app. And so in order to build virtually like any of our source code, we need to build a very deep dependency graph. And so bringing all these dependencies into Bazel was effectively a dependency of even building the iOS app in Bazel at all. So as Raul mentioned, we were previously using Cocoapods, which basically is the canonical way to manage a package in Bazel, or in Xcode rather. So that Cocoapods, for those of you who aren't familiar with iOS development or Apple-based stuff, it basically downloads the repository from GitHub or wherever, and then it integrates it into Xcode, which is the build system. So in order to get these dependencies up and running, we were like, okay, let's go ahead and take a look at what Bazel's doing. We found new HTTP archive. We found Git repository rules, this and that, and we started out by writing build files by hand. Quickly we realized that this was not going to be feasible for 50 external dependencies, and even if we were able to actually implement all this build file code ourselves, it's the last thing that we ever want to maintain in the world. Yeah, going back to Cocoapods again, Cocoapods is there's effectively 2 bits to Cocoapods. The first is the actual system that downloads and integrates your dependencies. That's like 1 bit that I think about Cocoapods. And then the other part is the actual pod spec. So in Cocoapods, there's this notion of a configuration descriptor, which includes all the source files, header files, compiler flags, and it even tells you what are the dependencies on other Cocoapods. So given that, what we realized is that we could take this pod spec, this Cocopod file that was previously used to generate the Xcode-based projects, and we could actually write out build files and integrate all these dependencies with Bazel. And so what started out to be a very trivial Python script that I wrote in like a day ended up being a massive Swift program over the course of a few months. And we ended up implementing Cocoapods for Bazel. And so yeah, Cocoapods for Bazel, what does that mean? The name of the program is called pod to build. The user actually describes the dependency with a very simple macro, and then we compile a build file based on the pod spec. And this macro was originally designed to be a repository rule. So we first implemented this as a repository rule. This would go right in your workspace file around all the other dependencies. And it looked just like this. It still has the same syntax today. We ran into a ton of complications with using external. First of all, as you heard from the other folks here today, adding several different services, whether that's GitHub, whether that's Google.com, Fabric, Foo.bar, whatever you have, you don't want your CI or your build system going out to all these external services that you don't control. And that introduced a ton of reliability and actual build performance problems. Developers were like, hey, this build's slow. And I was like, well, it looks like you're making requests to Foo and Bar, whatever. And so that was a huge problem with this. And then in our actual dependency management system, we actually like found a way to cache those outside of Bazel so that repository rule wasn't re-downloading. And on top of that, we had a lot of problems with Xcode and IDE integration using this. Xcode, just like if you have files in Xcode and you're taking them away from Xcode, it's basically going to re-index those files in every other file. So anyways, so back to bod to build. Like every other dependency in Bazel, like you do in a workspace, you have to flatten your dependency graph into the workspace file. And so you have multiple pods that depend on pods. In this example, pin cache depends on pin operation. So we have both of these new pod repositories declared in the workspace file. And so yeah, so this program, it was a pretty large undertaking. We ended up implementing the full Skylark syntax in a pretty functional Swift DSL. And we have our own downloading infrastructure to actually like download archives, unzip them, and it doesn't depend on workspace or repository rule. And so as of within the last like 30 minutes, it's now open source. So you can go. So yeah, you can go on GitHub right now, and you can see all of our commits from the very first one. And this contains all the logic that we're using to integrate over 50 dependencies into Pinterest right now. Yeah. So as the rocket scientist earlier mentioned, they did validation of their build. We're not building rocket ships at Pinterest, but I can tell you what we're doing is incredibly important. And we needed to make sure the builds were going to be the same. With all 50 dependencies, we actually wanted to make sure that we were building these dependencies the exact same way. And so it was pretty simple to achieve this. If you look at a build system as a set of inputs and outputs, you can reduce any build system to that basic fundamentals. And so we did this, and we used Xcode before, and so based on like a lot of private frameworks, we were able to expose all the inputs and outputs of Xcode. And in Bazel, we use the extra action API. And so, yeah, after that level of rigor, we were certain that we had the right linked frameworks, we had the right files with the right flags. We went through more rounds of validation. So all of our unit tests, all of our automation testing, we ran through. We ran the app through our internal dog food group. We actually sent the app out to our QA folks. We sent it out to Lodestone, and after all that rigor. For our program, we were able to ship a fully built app under Bazel without impacting the users. And so we were super proud of that. So yeah, so back. OK, right. So Bazel's supposed to be fast and reproducible. Choose to. Well, we at least got half of it right. The app was reproducible. Our builds were awesome. It worked. The users loved it, but it was actually reproducibly 2.5 slower than what we had. So that was a blocker. Like we had this great system, this great infrastructure, but we couldn't even give it to our developers because it was unacceptably slow. Like it was a total blocker. And so I started looking at this problem, and our team was looking at it. And Xcode's been around for 20 years. It's older than that actually. And so the fact that we were going to make Bazel as fast as Xcode just seemed like a total pipe dream to me. I was really doubting that we could achieve this at first, but we went back to the fundamentals and basically profiled at a system level to understand what Bazel actually was doing to the system holistically. And so we got a quick idea of what was taking the time. And on top of that, we actually added a lot of profiling and logging to Bazel, and whether that was in the Java code or the actual shell script rule implementations to find the hotspots. And as you all probably could guess, compiling our object files was the hottest and most expensive code path, the actual compiler invocations of Clang to produce the object files. So I'm going to give you a quick summary of how we sped this up, and it was a great success. But I'm going to get into the tricks that we did first. So in Bazel, for those of you who are familiar with the execution system, basically at the end of the day, the spawn strategies is going to execute a bunch of shell scripts, which does some stuff, and then that's going to execute Clang. So there's several layers in Bazel that actually are involved in running Clang. And so at the edge of this, the cross tool is invoking the XC run wrapper. And so in this script, there's actually a loop over a massive input, and it's doing like string processing in Bash, and not to mention that it's several shell scripts launching shell scripts. You have like wrap Clang, you have this and that running all these shell scripts, and basically by replacing all those shell scripts with a custom binary that was precompiled,
that saved 3 minutes off the entire build time, and that was going from like 9 minutes to 6 minutes or something like that. So that was that's a fundamental. That's a 3 minutes is a fundamental change when we're talking about 9 minutes. So the other main thing that we've heard before is that iOS uses a bit different of import semantics than other types of developers out there. The C++ folks and the C developers, this is totally different. So in iOS development, within the same package, when you import a header file, you typically import it as import header.h, regardless of the file system location of that header. And when you import from another package, whether that's a framework, a static library, a foo, or a bar, you import it as namespace / header.h. And so to actually implement this in Bazel, we were passing in hundreds of directories to clang. So clang is like getting hundreds of directories that it had to do a linear search across all of these directories every time it sees these imports. And so it's a pretty silly trick to fix this problem. Instead of querying the file system for headers every time doing this like ridiculously slow linear search, we put all the paths into a hash table. And so we basically dynamically generate these hash tables, and then Clang memory maps the hash table into its process, and it has constant time lookups for what used to be incredibly slow. And this actually cut our build time up in half. So yeah, I'm incredibly proud of this optimization. And yeah, so back to like the original story. Our original build time with Bazel was 9.5 minutes. Which was unacceptable for our developers. I know some people out there are like 9.5 minutes. That's unbelievable. Like ours is like 8 hours or whatever. But when you have a great system that's been optimized for so many years, you have to execute, and you have to get it to the same level of speed and performance that the developers were used to. And so yeah, in addition to what I previously mentioned, we have like all these extensions. We have Siri, we have notifications, we have this and that, all these different types of extensions that we're building. So we actually created a program that doesn't have any extensions. And this is a very simple optimization. Removed almost like it cut the amount of actions in half. We're at like 6,000 actions, and we're down to 3,000 actions by doing this. Removal of the DSIM generation and patching. Originally we were using DSIM to do debugging, but we're actually like remapping debug paths in Clang now, and then using Clang modules. So yeah, that's another like non-Bazel-y thing. But because of Bazel, we were able to use Clang modules pretty easily. And so I mentioned that there's still some stuff on the table right now. If you go on GitHub, I proposed that we add header maps into Bazel because it cut our build time in half, and that's a huge win. People that are using iOS development are going to have massive wins just by that patch, and also it also translates over to the C++ end of things as well. Yeah, the overall cross tool and spawn strategy, there's still about maybe like a minute or so of optimizations left in there that we're working on. So yeah, that's how we went full Bazel in a nutshell. And Raul is up next to talk about developer adoption.
So after a lot of work, we had we had something that built. We had something that matched our current build before. We got the performance from 2.5 back to 1. And the next step is let's take this exciting thing we've been working on and give it to developers. And so when we started to roll this out, we noticed some early wins that are really promising. And I kind of want to share some of them with you. First is our build speed and reliability dramatically increased. Clean builds were decreased by 11%. We started using Bazel tests to run all of our unit tests. Someone please work on the integration test runner. We no longer have it works on my machine issues. Developers have been able to, we haven't had a scenario where someone had a failure locally that didn't also occur on CI and vice versa. And a lot of our code generation tasks were automated as part of the build. And And then for our CI system, which was struggling, as I mentioned before, our PR builds are 27% faster. Producing our build artifact for the beta audience is about 45% faster. And our success rate improved from about 80% on our CI setup to about 97 to 100%. And this is an example, sort of screenshot I took of our beta build. And this is a screenshot from BuildKite. And basically, you can see it's 100% reliability. And another thing, if you're using Bazel, another thing to sort of throw out there is like you should also check out Nix. Nix is kind of fun to, because like Bazel can declare your entire build, whereas I know some people are using like Kubernetes and things like that to manage kind of the container environment around it. But if you're an iOS developer, you don't get that. So and because you have to compile on Mac hardware, so Nix actually allows you to sort of declare everything around the build and all the dependencies around that. But I have kind of a thing that I hate to break to you, but fast and reproducible is unfortunately not enough when you're giving it to developers. And the issues are really in the developer workflow. And we thought this problem was solved. We put a lot of work. We have our own custom fork of Tulsi. We've tried to maintain patches. We tried to upstream a lot of things. But I think like one of the pains that we face, and I'm pretty sure it's pretty common, is sometimes some of the best practices around these things and around these tools are not really well known. So for instance, we started getting questions like this, like, how often am I generating this project? Why aren't we checking in the project? And what are these like the number of targets I can pick from an Xcode have doubled. Now I have all these IDX targets. I'm not really quite sure what these are. Which boxes should I check if I'm adding files? And then once you get past the education piece, then you actually have other issues. We noticed, especially with Xcode 9 coming out, indexing for us was noticeably slower. Our autocomplete behavior, it's like it worked sometimes. Like it might have worked on the main app code, but then for like gen files, it was like inconsistent. So there's like some parts of Bazel that are like not really playing well with Xcode. And there's also like certain features that were missing that we've actually implemented. Like we implemented like the static analyzer using the extra actions API. And our developers really missed the progress bar. We're like, just go in the build log. Just look at the log. It's outputting. It will say it's like 5 out of 300 actions. And then when it gets to 299, it'll go to like 6 out of 2,000 actions. And I'm like, I promise you there's an upper bound. It will eventually reach its limit. And I tell them why, and they're like, I was like, it's learning about the build as it goes. But you know, it's kind of a hard thing to convey. And you know, I don't want to rag on Tulsi too much because the reality is that Xcode is designed with the assumption that it's your configuration editor and build system. It's designed around these assumptions, and that's how those features work. So like at best, what we're going to get is parity. And I think the problem right now is like we're missing that last kind of compelling bit on the iOS integration experience, like things like having remote caching fully working, that make it like the obvious choice to why you would actually take maybe some of these issues or some of this instability for build speed wins. So this is kind of new. In the last week and a half, we've embarked on a project that is codenamed Baja Blast. If you're not familiar with Baja Blast, it was discontinued in 2013, and it was only available at Taco Bell. We only called it this because the rest of our team was working on a project called Code Red, and we just made fun of them about Mountain Dew. And so Baja Blast, it's a refreshing take back to a pure Xcode experience derived from Bazel. And the idea is that like we love the wins we got on CI, and we think we can continue to improve them. We like the stability. We like having all of our configurations explicitly defined through build files and BZL files. But we need to figure out the local developer workflow. We need to actually improve that experience before like subjecting our developers to it. So this project allows us to maintain the wins on CI. The editor experience is consistent with what people were used to before. And as soon as we get things like remote caching, remote execution, I think we'll kind of go back on this and maybe see where Tulsi's at and see how we can actually make the integration more compelling. But how does this work? How are we doing this? We're actually taking some inspiration from Tulsi, which is to use the Aspects API. If you're not familiar with Aspects, is everybody familiar with Aspects? Pretty much, mostly, maybe. OK, so Aspects allow you to basically create a shadow build graph. So you can say for any sort of build action, you can create a shadow set of actions. So in this case, you can use the aspects API to extract all the build information. So all the targets, all of your compiler flags, whatever you need. And we load this up into a program written in Swift, because we write everything in Swift, and except our app. But and then we translate it to the specification that's defined in Xcode Gen, which mirrors Xcode pretty well. And then we actually link in the Xcode Gen framework to generate a pure Xcode project. And we're still playing around with this. We have some of this working, and we're hoping to open source this probably in the near future. But in conclusion, incremental adoption is definitely possible on iOS if you're willing to maintain the glue layer in the shell scripts and copy the headers. Reliability is free, but performance isn't. Modularity still matters. I think a distinct focus on like the performance, especially, I think what would be great is to actually have maybe analysis of the same project in Xcode and Bazel in like a sort of a larger project, and kind of make sure that as we do releases that they're at parity. Migration tools are essential. They're essential. Like, I can't stress this one enough. Like, I mean, we're lucky enough we had 3 engineers that could write 2 transpilers that and a validation system to ensure that we were actually shipping the same thing. So if you're starting off a new app, it's probably not too hard. You're probably just like, glob everything and name it app, and you can build it. But for us, for any existing app, for any mature app that's looking to get these wins, it's really essential to have these tools available. And to recap, fast and reliable isn't enough. Workflows matter. Think about ways that developers outside of Google actually develop. Like, they have external dependencies. They have certain workflows or tools that they're used to, and we need to figure out how to migrate them from those to a pure Bazel environment. And optionally, like, I know I talked about the Xcode integration a bit, but I think we should also look at other editors. We should look at like how can we integrate into things like Nuclide, how we can integrate into things like AppCode or other systems. How can we make Bazel the de facto build system and decouple it from the editor experience on iOS? And this slide came too late, but that's where I was going to say that the Baja Blast was going to be open source soon. But thank you so much to Google for having us. We're happy to be here.